Hello class, welcome to topic 3.5, the circle, and what we're going to look at is just 3 or 4 concepts related to the circle. We are not going to investigate in detail this shape, it's just some aspects of the circle. And the first aspect we're going to talk about is the radian measure of angles. So, as we may know, a circle can be divided into 360 parts, etc., etc. And when you take one of those parts, let's just look at this one. The angle enclosed these two radii, this particular angle is called 1 degree, and therefore the degree is a unit of measurement for angles. Okay, and this is the one that you know since primary school. And now we're gonna look at another unit of measurement for angles, which we call the radian. Now, why is the radian important, or why did people think necessary to actually create another unit of measurement for angles? Like, I mean, the question was this: why was not a degree enough? Why do we have to invent another unit of measurement for angles? And the reason is more or less the following. You should appreciate the fact that it looks actually kind of random to decide upon this unit to be you know to what I mean is this: when people defined the degree, it looks kind of random to divide the circle into 360 parts. That's what I was trying to get at. Okay, like some people can ask, why 360 parts? Why not more, or why not less? Why did people think that 360 parts was like the ideal or something like that? Because it looks kind of random or arbitrary to divide the circle in 360 parts and call each one of those parts 1 degree in regards to the measurement of the angle. It looks kind of random and kind of arbitrary. So there's a supposedly better way. I don't know if it's really better. I'm a little hesitant about that. So there's a better way to define a measurement for angles, and that way is through the radian. It's gonna sound a little complicated at first, but you have to get used to it. Okay, so we're gonna start by giving some context, very simple context. So let's talk about a central angle. What is a central angle? When you have a circle and you draw an angle in the following way, like you have the center of the circle, and when you draw an angle such that its vertex is located at the center of the circle, this is the vertex. Remember, the vertex of an angle is this little spike, or this little point in here, this precise point. So when the vertex of the angle is located at the center of the circle, then we say that this particular angle is a central angle. So that's what it means. Let me give you an example of an angle which is not central. If I draw the center and if I draw this angle, this is not an angle, this is not a central angle, because the vertex of the angle is not at the center of the circle. It's a very simple idea. Okay, next concept. The arc intercepted by a central angle. So once again, if I have a circle and if I draw a central angle, you should notice that the in this case the radii, remember radii, that's the plural of radius. Radius, this is a radius, these are radii. So I was saying, you should notice that these two radii that are the sides of your central angle cut a little part of the circumference, which is this blue part. Okay, it intercepts. a little bit of the circumference of the circle, which I'm highlighting in blue right now. And this is what we know as an arc. And in particular, this arc is the one intercepted by this central angle. Let me draw another central angle. Well, right in the circle, a slimmer angle, central angle. And the arc that this angle intercepts, or that this central angle cuts, would be this little bit. So this is another arc. So far, pretty simple stuff, right? So we have two things down. Now, the third concept, the core of this lesson, the definition of the radian. So what is a radian, guys? A radian, like I said before, is a unit to measure angles, just like the degree. It's just like the degree. And how does it work? If we know that the degree is basically dividing the circle into 360 parts, and then one of those parts is 1 degree, then how does the radian work? Well, the radian works in this way. We say the following. If you have a circle such that, and I'm gonna say stuff, all of this stuff very slowly so that you get it. Pay attention to every single word, because from my experience, most students do not understand this definition the first time they hear it. So listen carefully. If you draw a circle and you draw its center, and you draw a central angle, which I'm gonna do right now, in such a way that the arc intercepted, well, this is the central angle. If you draw this central angle in such a way that the arc intercepted by this central angle, if this arc, well, not the arc, if the length of this arc intercepted by this central angle is equal to the radius of the circle, I'm gonna draw an R here in order to represent the length of this radius, and I'm gonna draw an S in here in order to represent the length of this arc. If you draw an angle, a central angle, in such a way that the length of this arc intercepted, is the same, equal to the length of the radius, then if you have done so, what you have drawn is an angle of 1 radian. That's what 1 radian means, guys. That's how you draw a radian. Well, no, an angle of 1 radian. Let me do it once again. This time it will be faster, right? I'm gonna draw the same. I'm gonna do the same thing one more time. If you have a circle, you have its center, and if you happen to draw, I'm gonna do it now over here. If you happen to draw a central angle in such a way that the length of the arc intercepted by such central angle, the length of this, which I'm going to represent by S, happens to be the same as the length of the radius, which is this bit, or this bit, it's the same, right? This radius is the same as the radius. If this S is equal, the length of this arc is the same as R, which I can actually write in here. If S is equal to R, then we have drawn an angle of exactly one radian. That's how it works. That's how it works. You need to pay attention. You need to pay attention to the words that I say, and you need, if you really want to understand the definition, You have to do it later on your own. Like try to, let's say that try to explain it to somebody else or to yourself or to the wall. Just talk alone, okay? And say, okay, 1 radian is this. If we have a circle and we have a sand, blah blah blah. Do the whole thing I did on your own, 3, 4, 5, 6 times, 6 times until you get it. Until you get it. If you don't do that, believe me, you're not gonna understand the definition if you don't do it on your own. So that's how big 1 radian is. All right. So now we know what a radian is. Now, some people may be asking, so what's up with this definition? It looks kind of weird, right? Like, why do we need to define a new unit, which we're gonna call the radian, which is obtained in such a weird way? Well, one of the explanations that most mathematicians argue for is the following: that this unit defined in such a way is not arbitrary. Why not? Because you are actually using a property of the circle itself, in this case its radius, okay? You're using the radius in the definition of the radian, because if you draw a central angle such that its arc measures the same as its radius, the radius of the circle, then this is 1 radian. So you're using an intrinsic property of the circle, which is its radius, in order to define the radian. So this is much less arbitrary than the degree. You see, it's more, let's say it's more aesthetic also. You should appreciate how, I mean, at least to me, this is a pretty aesthetic definition. It's a very nice definition, a very mathematical one. It doesn't rely on a seemingly random number. Like why 360? It's very very random, you see? And the radian doesn't have that downfall of being kind of random, so to speak. So that's why, and for many more reasons, okay, that's why people came up with the measurement of radian. There are more reasons, which I'm not precisely, I don't want to tell you right now about the other convenient reasons to use the radian. Okay, now let me tell you about one theorem, which we're gonna use in the next bullet. So this theorem is the following. It's a very simple theorem. If you have two circles of the same size, although they don't have to be the same size, but let's just keep them the same size. And if you draw two different central angles, I'm gonna draw this central angle in here, and I'm gonna draw this central angle in here, and I'm gonna make this angle twice as this. Now let me give names to this angle, to these angles. I'm sorry. Let me call this angle 1. Let me call this angle 2. And this arc, the length of this arc will be called S1, and the length of this arc, well, let me draw them in blue. The length of this arc is S1, and the length of this arc is gonna be S2. And remember, I supposedly drew this angle to be twice as this. Okay, so the theorem goes like this, which I'm not going to prove. I'm just going to state it. I'm just going to state the theorem. If you have two central angles, each of which intercepts its own arc, then the arcs are proportional to the angles. I'm going to repeat. The arcs are proportional to the angles. What that means is this: if this angle is twice this angle, then this arc will be twice this arc, which makes a lot of sense. Probably you could have guessed that on your own, because it's a very intuitive piece. It's a very intuitive fact, but yes, it works, and it can actually be proven. And if the angles are proportional to the arcs, or vice versa, if the arcs are proportional to the angles, then we can write the following equation: a2 over a1 which is the division or the ratio of A2 to A1, will be the same as the ratio or the division of S2 over S1. Or you could have done it the other way around. It's pretty much the same, right? Well, not pretty much. It's the same. Either way, it doesn't matter. That's what this theorem is about. Arcs are proportional to their central angles. Fine. And finally, guys, with this theorem that I just proved, we can get the equivalence between radius and degrees. If both of these things are units to measure angles, then clearly there must be an equivalence, right? It's like when we say that 1 kilometer is equal to 1.609 miles. That's an equivalence. I'm saying that one of these things is equal to 1.609 of these units. So this is an equivalence, and there should be an equivalence between radians and degrees. How do we get it? We're gonna use this theorem, and I'm not going to raise this theorem because I'm gonna use it, and I'm gonna get the equivalence between radius and degrees over here. So let me do the same. Let me draw two circles of equal size, center, center. And in this circle, I'm going to draw an angle of 90 degrees, which is 1/4 of the whole thing, right? This angle in here is 90 degrees. And so this is 90 degrees. And this angle, the central angle of 90 degrees, intercepts this arc, which is 1/4 of a circumference. Now, this quarter of a circumference, since we know how to get, oh, by the way, I forgot something. Since this is the radius of the circle, I'm going to label this little bit as R. This is the radius, R. Okay, now let me go back to what I was doing. If this is just 1/4 of a full circumference, then it can be proven that since the full circumference is equal to 2 pi r, do you remember that? Full circumference of a circle, what is the measure of, how much does it measure? It measures 2 pi r. Then 1/4 of that full circumference will be just pi r over 2. If you divide this by 4, this is what you're going to get. So this arc, this blue arc measures pi r over 2. That's it. Okay, now let me go over here to this other circle and let me draw another central angle. This is the radius of the circle, so it should be labeled r. So let me draw another central angle. In this case, I'm going to draw 1 radian. So if this is 1 radian, guys, therefore we should have that, by definition, by the very definition of radian, we should have that this intercepted arc should measure the same as this radius. So this is also r. This arc, the length of this arc is r. Fine. It's pretty simple stuff, right? And also we have that this angle is 1 radian. I'm just gonna write 1 rad. So this is 1 radian, and this is the length of the intercepted arc. Fine. Now let me apply this theorem exactly as it is. I'm gonna apply this equation. The ratio of both angles, in this case this angle over this angle, I'm gonna write it down, 1 radian over this angle, which is 90 degrees, should be equal to the ratio of the arcs, S2 over S1. So what is S2 in this case? It's R over the other arc, which is pi r over 2. Okay, and I'm gonna ask you to stop the video, and finally I want you to simplify this whole thing. I want you to simplify this fraction as much as possible, and then isolate 1 radian in order for you to give me the equivalence of 1 radian and degrees. Just simplify this part and keep pi as the symbol. Do not represent pi as 3 point whatever. Keep pi as a symbol. Just simplify this thing and isolate this quantity, 1 rad. And well, tell me what you get. That's it for today.